Most structural engineers today use finite element software to design frame structures like warehouses. But these programs are complicated and can be challenging to start with, especially when you have little experience. That's why in today's video I'm gonna show you exactly how to model and verify a 3D steel framed structure in the FE program SkyCiv. Here's what you'll learn in this video. First, I'll show you how to sign up to SkyCiv and use it for free for 30 days. Next, we'll learn how to model the 3D frame structure with beam elements and tension members as the wind braces. You'll learn how to define supports, how to apply area loads, and how to create load combinations. I will then show you some tips how we can check that we actually modeled the structure correctly. And then finally, we'll use the SkyCiv design tool to verify all steel sections according to Eurocode 3. Now, before getting into the video, let me quickly introduce myself. Hi, I'm Laurin. I'm a full-time structural engineer based in Munich, Germany. And for the past 3.5 years, I've been building Structural Basics, which is a learning platform that teaches professionals and students things like load calculation, engineering mechanics, and structural design of steel, timber, and reinforced concrete elements. Now let's start the computer and let's get into the video. First, we need to sign up to SkyCiv and activate our free trial account. To do that, go to skyciv.com/Laurin or click the link in the description below. All of my followers get a 30-day free trial instead of 14 days. So thank you SkyCiv for sponsoring this video, which is allowing me to teach my community how to use finite element software and giving my subscribers an extended trial. Next, fill out the personal information and click on register now. Great, we're now logged in and ready to start modeling the 3D frame structure. Before modeling, let's quickly look at the structure that we're going to model and verify. This is the 3D warehouse. We're going to use HEB 500 steel beams as the beams. Then we're having also HEB 500 as the columns. Then we're having these rafters between the beams, which are transferring the vertical loads to the beams on the frames, which are HEB 180s. And then we are having these wind braces, which are CHS profiles, and they are stiffening the 3D frame structure in the longitudinal direction. Before now modeling it, let's quickly also understand the 2D static system of the frame structure. Because if we don't understand the 2D static systems, we won't understand it in 3D. So we're having two pin supports and we're having two moment stiff corners. So if you have a horizontal point load at one of the corners, then these moment stiff corners, they're resisting this load and transferring it down to the pins, which are the foundations. Then you'll also learn how to apply these line loads on the most outer beams, which are basically the horizontal wind loads in the longitudinal direction. And then we'll also apply area loads like snow and dead load. To start modeling, we click on Structural 3D. Then we click on Start New, and now we have an empty canvas. Now, before modeling the columns and beams, we first need to create materials and sections. So we click on Materials, then on Database. We click on Metric, because we are in Europe. Then we click on Steel, European Standard, so that is Eurocode. And then for this tutorial, we are going to use a grade S235. And the thickness will be more than 3 millimeters but less than 16 millimeters. And now click on Submit. And then finally we have to click on Apply, otherwise the material is not going to be saved. Okay, great. We now go back and create our sections. So click on Sections, then we click on Section Database, select European, Steel, category. We want to create an HEB 500. So we click here on HE and then we find HEB 500. Here. And then we select the material that we just created and click on Submit. Okay, great. Now let's do the same thing for our rafters and our wind braces. Now to create the frame, we first create nodes and we connect the nodes with our beam and column elements. So to do that, we click on nodes and now there's two options we can choose from. We can manually enter nodes with coordinates, or we can use the pen tool where we can actually select in the canvas our nodes. Let's do both. First, we create the first point with the coordinates. So let's click apply and now we have our first point. And now we could go on and say y-axis is 7 because that's the height of the frame, and then set the 0 and x is also 0. But let's try this pen tool. Click on this pen here, over here. We can also apply a grid. In our case, since we have 16 meters of width and 7 meters of height, we choose this grid and also use the XY plane because that's where we kind of draw our frame. And then on drawing options, deselect create members. For now, I'm gonna show you why, because we're creating the members afterwards. All right, and now we are selecting our second. So let's go up 2 meters, 4 meters, 6 and 7 meters, and then just select this one. And now it created the second node. And now let's create the third node, which is 16 meters away. And then the fourth node, which is down here. Great, now we created all 4 nodes for one frame for now. Click apply. Oh, this is the fifth node, so no. And now we can go back and we can create our columns and beams. To do that, go to members, new member, and now again we can do it manually, like connect node A with node B. So we connect node 1 to node 2 with the profile HEB 500 and click apply. Let's use the pen tool to do it for member 2. So we click on the pen tool and then we click here under drawing options on create members. And we click on 2 and 3. And now we created our beam. And now let's just continue with 4. And now we created our 2D frame. Next, we're modeling the supports. So click on supports. And as I showed you previously, we want a 3D pin support. So click on this one. Again, we could say 1 and apply. And put in 4 and apply. No, this was the wrong one. Click on 2 and then select 3D pin support and apply. And you can see that the support is now changed from a moment stiff support to a pin support. To save time, we copy and paste the frame one time and then we model the rafters in between. To do that, hold Control and then select all elements. And then right click on one of the elements and click on repeat or type in Control and D on your keyboard. We want 1 repetition, distance between repetitions is 5 meters and we want to do it in the Z axis. And now click on submit. And now we duplicated our frame very quickly. Now as a next step, we are splitting the beams. So we get the nodes for the start and end point of the rafters. Okay, so click on both beams by holding Control and then clicking on both. And now right click and we click on split members. Now click on divide member into equal parts 4 and only create nodes. If we don't have this toggle on, then all the members are split into 4 parts. But we actually just want to create nodes, because otherwise we're getting some problems in the buckling analysis later on. So click on split, and you can see the newly created nodes, and now we can model our rafters. To do that, again, click on members, new member, we say node 2 and node 6. It is continuous. Section ID is 3. And node A fixity is pin, and B is also pin. Click apply. Now we're repeating this for all of the other rafters. Alright, so now as the next step, we are copying and pasting one frame with the rafters 6 times. So hold Control, select one frame, and then Control and select all of the other rafters. Right click, repeat. Number of repetitions 6, distance is 5 in the Z axis. Click on submit. And now we created the full 3D structure. We can check if we modeled all members in the correct size if we click on this open 3D renderer, and it looks actually pretty good. Again, deselect the renderer, and now one thing is missing. We need to model the wind braces. So we need to model them in the first spans of the rafters, but also here in the longitudinal facades. Alright, click on member again, click on truss, it's a tension member, node A is in this case 2, node B is 5, and click on apply. Now we do the same for 1 to 6. And we can select this now and copy it to the other side. And this is the x-axis, 16 meters, number of repetitions 1. And here we go. Control and click on these wind braces to then copy it on the other side. Repeat. Now I'm unsure about, so it's 5, 10, 15, 20, 25, 30 meters, 1 repetition in the Z axis. Submit. And now we have the wind braces also over here. And now we only are missing to model the wind braces in the roof area. Click on member, nodes 2 to 12, tension member, apply. Node 9 to 6, tension member, apply. And we can now again copy and paste 3 times. The distance 16 divided by 4 must be 4 meters in the x-axis. Alright, great. Now we're selecting all of these wind braces. Click on duplicate, on repeat. Number of repetitions 1, distance 30 in the Z axis. Submit. And here we go. Now let's check again the 3D render, it's always helping. And here you can now see that we made a mistake actually. So we use the HEB profiles to model the wind braces, which is not correct. So we go back to the members and we can actually also see it with the color. So select one of them and then we can just select the CHS profile. And one way to quickly do it is if we open the data sheet. And now we can see we should see all of the tension members here. And we can actually change the section ID to 1. Copy, and then I can select all of the other tension members. Paste. And now they should all be CHS profiles. Click on apply. And now we can verify this again with the 3D render. And now it's looking a lot better. All right, great. As a next step, we create and apply the characteristic loads like dead, snow and wind loads to our 3D structure. As a first step, we activate the self-weight. To do that, click on self-weight, -1 in y-axis. We call it SW1 and then click on and then apply. Now the self-weight is included in our loads. Next, click on area loads and insert the 4 corner node IDs. So click back on our analytical model. We have 2, I believe this is 3, 56 and 51. So click on area loads. Type is one way, corner IDs 2, 3, 56 and 51. Pressure magnitude, the dead load will be 2.5 kilonewton per square meter. Okay, so we have to also say minus 2.5 because the y-axis is going upwards. Column beam direction, we're applying the load to the rafters and the rafters are going from 2 to 3, that's correct. And then the load group, we just call it GK, which is usually used in Europe for the characteristic dead load. And then click on apply. And we can see that the dead load is created. By the way, kilopascals is the same unit as kilonewton per square meter. And now we just repeat the same process for the snow load and we apply a snow load of 2 kilonewton per square meter. Alright, so now for the wind load in longitudinal direction, we are applying a line load. So click on distributed loads. Distributed loads, member ID is 2, so it's this beam. Start x-axis. So now we need to define the 4 kilonewton per meter and we are defining it in positive z direction. So this can be left empty, here it's 4 and here it's 4. Start position 0 from the start to the end, so 0 and 100%. Load group, WK, which is used in Europe for the characteristic wind load cases. Click apply. Alright, and now we defined all 3 loads that we're going to use in this tutorial. This is not going to be a tutorial on how to calculate loads. We only use these 3 load cases. Of course, there are much more load cases in a structural design of such a warehouse, but we keep it simple in terms of loads. Now, as a last step, we need to create load combinations. To do that, click on load combos, and now we can define load combinations manually. So we can factor different load cases and we can actually create also load combinations automatically with SkyCiv. I personally always prefer to do the load combinations manually because then I know exactly what load combinations I created, but I also want to show you how you do it automatically. So click on design codes, then up here to Europe, then Eurocode 0 and display. And now you can actually see all of the load combinations that are going to be performed. Save file, and then we click on import. Dead load is unfavorable, everything is unfavorable, and then click on import. And here we have all of our load combinations. Click on apply. And yeah, now we're ready to verify our structure. Once I'm done modeling and applying the loads, I like to do a few things before verifying the actual structure. One of those things is checking the deflection. Click on solve, on OK, and then on displacement. And now I want to actually look at the deflected shape if it looks fine for the dead load. And the dead load is acting downwards. Yes, this looks actually fine. And the columns are deflecting outwards. And the rafters downwards. Here, this I need to investigate a little bit more, if it's a moment stiff connection or a hinge connection. But overall, this looks fine. Now let's look at the wind load. And it's also nice, only this tension member is activated, which is fine. Next, I also like to check the bending moment diagrams to see if all hinge connections have no bending moments and all moment stiff connections have actually bending moments. Click on moment and then on the dead load again. And now you can actually see that the rafters don't have any bending moments, which should not be the case. They should have a bending moment. The bending moment should just be 0 at their supports. So now we go back and investigate what we did wrong here. Go back to model. Okay, so there are two things I'm currently thinking about that could have gone wrong. One thing is that we didn't define the hinge, the connection type of our rafters correctly. So if you click on one of the rafters, but actually we defined the connections as pins, so that should be fine. The other thing that I'm thinking about is that we defined the loads incorrectly, that we applied the area loads on our beams instead of the rafters. So we can quickly check that if we click on the load and then do the column beam direction in the opposite direction. So click on this change to using the other direction, and let's do it for load 2 as well. Click apply. I didn't do it for load 1. So click this one and then apply again. And now click on solve, linear static, and now we investigate the bending moment again. About z-axis, I want to investigate the dead load. And we can actually see that the bending moment diagram looks like I want it to look like. And also the frame moment diagram looks fine, and the columns as well. All right, great. So now we can do the last step and design and verify our steel elements. Now we can finally design and verify the structural elements, and that's quite easy in SkyCiv. Click on design, start new code, then we click on steel member, Eurocode 3, click on start, and now click on check. Now we can see all of the utilization ratios of the different members, which have those IDs here. And we can even see the utilization ratios of the different design checks. So, and if you click on the eye icon, you can read which check it is. The check ratio of members subject to combined action, resistance of cross sections. One thing, however, you need to be careful of if you're new to finite element modeling and designing your elements in an FEA program. For elements that are prone to buckling, you always need to check which length is actually used. And if you remember in the beginning of the video, I said to you, we don't want to split the actual elements, but we want to create new nodes. But if you actually split the elements, and that happens in the beginning when you're getting started with finite element modeling, and then you need to check actually the buckling length that was used in the design calculation. And in SkyCiv you can see that if you click on members, and then you can see here the length that is used for the buckling analysis. And let's say this is a column, but this is a beam. And we are having 4 meters out of plane, and then we have 16 meters for the buckling analysis in plane. And this is exactly how it should be, because out of plane we have the rafters that are holding the beams together, but in plane we have the 16 meters. And if you split the element in 4, you would also have a 4 here. But the nice thing is actually that you can change it here as well. So if you have split it in 4 parts, then actually change the buckling length to 16. This is well done here in SkyCiv. And we can go back to results. We see the summary, but we can also see the governing utilization ratio, which is 80%, which is quite okay. Then finally, we also need to export the results of our analysis, because we always have to write and create reports as structural engineers. And that's also something that's very easy to do in SkyCiv. We click on summary, and now you get this really nice report with all of the section properties, material properties, and also the design capacities, and then finally the utilization ratios and the design verifications. Now to download this, simply click on download PDF, and the PDF is now downloaded, and you can attach it to your design report. Alright, this is how you model and verify a 3D frame structure with a finite element program. If you liked the video, then I would really appreciate you subscribing or liking the video. And please also let me know in the comment section below if you like this video and if you want to see more of these videos. And lastly, thank you SkyCiv for sponsoring this video. I see you on the next one.